So this is the final lesson in our whole 5-week series on binary maths, and I just want to revisit here the meaning of fixed and floating point numbers. So this lesson is a recap of things that we've done before, and I just want to look at how we represent binary, integers, fixed point numbers and floating point numbers, and then there's a chance that some discussion topics might come up, so I quickly want to review what you might say. Here are some technical terms that you should know. I'm not going to read them all out. You should have notes on what each one of those terms mean, and if you get the opportunity in the exam, you should show that you understand what those terms mean. A lot of what we do when we're converting to and from binary is to use a conversion grid, which gives us the position values of each of the bits. In a binary conversion grid, all the position values are powers of 2, and they mean slightly different things in the different types of binary number that we've learned. So in what we call an unsigned binary, all the position values are whole numbers and they're all positive numbers. In a 2's complement number, the first position, that is the most significant bit, has a negative value. And in a fixed point binary number, some of the positions are fractional values. So how does the computer know which of those methods is being used for a particular binary number? Sometimes it's due to the hardware and the way that the processor itself is built, but more generally it's because of the way the software has been written, and the same computer will use all 3 methods plus floating point depending on what software it's running. So let's quickly look at how binary integers are formed using the 2's complement method. If we need to convert a 2's complement number from binary to decimal, we write in the position values, they're powers of 2, and we write them above each bit. And remember that the first one, the most significant one, is negative and the rest are positive. And then we just add together all the position values where there is a 1. So this is 65. And this is minus 63, because we are starting with a minus number and then adding to it. And just to remind you, if a 2's complement number begins with 0, it's a positive number, and if it begins with a 1, it's a negative number. And if we're converting a decimal number to binary, we do the same thing in reverse. We work out what powers of 2 are needed to make the number, and then we put a 1 into the grid wherever we've used that number. And one way to do that, if it's too complicated to work out in your head, is to work down the grid from left to right, subtracting wherever you can. And if we need to turn a number into a negative number, and this is the easiest way to make a minus number, I think anyway, we make it in as an ordinary binary number. Let's say we wanted to make minus 40. So we make 40, which is 32 plus 8. And to make minus 40, we flip all the bits. Can you look down the page? Wherever there's a 0, I've made it into a 1. Wherever there's a 1, I've made it into a 0. And then, this is very important, you add 1 to the end, which, because of carry bits, has changed the number like that. And that's it, that's all that you do. So let's look at a worked example. Supposing we had to show minus 31 using 2's complement. The way I do it is to do 31. There it is, 1, 1, 1, 1, 1. And then I would flip all the bits. There we are. And then add 1. Increment the lowest bit. And there it is. And let's just check that we've got the right answer. Minus 128 plus 64 plus 32 plus 1 is minus 31. But it's easier to do the flipping and incrementing than to work that out. We'll also need to know how to convert fixed point numbers to and from decimal. So in a fixed point number, the point tells us the position values, and the position values to the left are integers and to the right are fractions, and they're all powers of 2. So you just start at 1 and then you halve them, 0.5, 0.25, 0.125. The fixed point tells us what the values are. So we put the bits into the grid and then we add every position where we see a 1. So this is 7.25. Similarly, if we're turning a decimal number into fixed point, let's say 12.5, we add together the powers of 2 or the position values that make that number, and then we write in the ones. They might tell you where the fixed point is, or they might ask you to work out the optimum grid to use. But in either case, in this instance, for instance, there's a 0.5, so you need at least one place after the point. And negative fixed point, if I wanted to create minus 12.5, for instance, I've got 12.5, so to make minus 12.5, I flip all the bits, and then I increment the least significant bit. Up to now I've been saying add 1, but it's not really add 1, it's just increment, make 1 bigger, the smallest number in the grid. So if I do that, that's what happens. So here's another worked example, minus 8.25. Here's 8.25. Flip the bits and increment the smallest bit, the least significant bit. And there's our answer. Minus 16 plus 4 plus 2 plus 1 plus a half plus a quarter is minus 8 1/4. And we also need to be able to convert between fixed and floating point. And if we combine that with what we've just done about converting fixed point to decimal, then we've got the entire repertoire of all the different conversions we might be asked to do. Now remember that a floating point number is made out of a mantissa and an exponent. And I couldn't resist this picture. It's all about counting the hops, basically. All the work that we do with floating point numbers, we're counting the hops. So let's recap what we did before. If you've got a floating point number and you want to convert it to a fixed point number, a floating point number is made of a mantissa and an exponent. You put the point into its position in the mantissa, that is 1 in from the left. Then you work out the value of the exponent and you hop the point to the left or right that number of places. So here's a final example. It's a floating point number shown as a mantissa and an exponent. The point is 1 in from the left of the mantissa, that's where it belongs, and the exponent has a value of 2. So to create the fixed point number, we hop the point 2 to the right, and that's our number. There it is. Because we know it's a fixed point number, and because we know the position of the point, we can work out the column values. And remember, we're using 2's complement, so the most significant bit is negative. So it's minus 4 plus 1 plus 3/4, 0.5 and 0.25. Incidentally, if we had to show the final answer using a full byte, which could happen, we just fill in the extra gaps with 1s. I know that sounds funny, but if we're doing a negative number, we fill in the gaps to the left of the number with 1s. And obviously with a positive number, you'd fill them in with 0s. And it still has the same value. That's just how 2's complement works. So if you worked out the value of those two numbers, they would both have the value minus 2.25. So they may tell you in the exam how many bits you've got to use in your answer. All right, so that's the last of the examples of this. Go back and revise if you don't quite get it yet. And you should also be able to convert in this other direction. They give you a fixed point number and you have to turn it into a floating point number. And remember what we do. We find the mantissa, we place the point, and then count how many hops to go back where we started. And that gives you the exponent. So let's look at an example. So let's look at an example. Here's a fixed point number, and it's a positive value because it begins with a 0. And the first thing we've got to do is find the mantissa. So because it's a positive number, the mantissa will begin 01. There it is. So there's the mantissa. We've already found that then. Now all we've got to do is find the exponent. So we put the point in its standard position and 3 hops to get back where it started with. So our exponent is 3. And that is literally it. The only complication is if you've got a negative exponent, you have to hop to the left and that will create empty spaces. Remember what I've already told you, we can fill in empty spaces with zeros or with ones, depending on whether it's a positive or a negative number. Okay, so now you understand how to convert between fixed and floating point numbers, and you use these skills, and we've also learned how to do normalization and how to do addition of floating point numbers. Sometimes they ask you to briefly discuss some of the issues. I don't think it'll be a long answer question, but they might ask you to discuss the advantages and disadvantages. So let's just have a very quick look at that. A lot of the advantages and disadvantages relate to underflow and overflow. Overflow is when you haven't got enough range to represent the large numbers that you've got. The number is too big, or a number falls off the left of the grid, or there's a carry bit with nowhere to put it. And underflow is when you haven't got enough precision, so you're trying to represent a fraction that's too small for the available position values. For instance, if you're doing a binary shift or something and a number falls off to the right of the grid. Now, fixed point is particularly prone to this problem. It's the simplest and fastest way for the processor to store fractional values, but you might end up not having the range or the precision that you need for the particular numbers in each case, and so it's got a bigger chance of overflow and underflow. Floating point, however, allows you to set the range and the position values each time, and that reduces the chance of getting those overflow and underflow errors. But on the negative side, it takes a bit of extra processing, so it slightly slows down the calculations. Okay, so your next steps now are to make sure you've got revision notes on all of these topics, and actually also to have those topics in your head, because we're going to have a test next lesson and it will go into all these subjects to do with fixed and floating point numbers. So I'll see you in class for the second mini mock of the year. All right, bye for now.